programming or multi-objective programming and things like that, right? So as I was saying just now, we would now be concentrating only on linear programming problems. Okay. Now, why we call it linear programming, I think though I have explained it, still I'll repeat it again. So, or we call it as LPP, linear programming problems. See, there are three terms, three words in this term, okay? Now, problems, we'll start from here, okay? So problem means you have a real life situation, okay, in which certain decisions need to be taken, okay? So your decision maker has come to you to resolve his problems, and what you will be doing is that you will be, as we do in modeling, right? So we'll be studying the real life situation, real life problem. We'll be converting it into a mathematical problem, or we'll be converting it into a mathematical model. Okay. Now, the term programming actually, what does it mean? Huh? Can anyone just say, what do you understand by programming? Those of you who have studied computers, you've studied various languages also. This is the very first thing that we must know. What do you understand by programming? Whom do I expect the answer from? Akanksha?
Ma'am, may I?
Yeah, sure. Anyone, most welcome.
Ma'am, in programming, we basically change a particular question or whatever we are asked to do in the form of a code. And with the help of that code, we can use that code to solve other problems of the same kind as well.
Okay. And anything else apart from what Dipanshi just said? Any improvement on this? Now, before you do the coding, what do? You don't just start away with the coding. Once you are given a problem and you have to program it, before writing the actual codes, what is done?
Ma'am, we identify the variables.
No, you've identified the variables. Once you've made the model, you've identified the variables. Come to the programming part now. Now, before you actually start writing the codes, do you do something else?
Then we first imagine it practically, and then we imagine it in a real life situation, and then we turn it into a code.
No, you don't directly. You directly turn the problem into code. और कुछ नहीं करते. You formulated the problem, fine. You also just said this.
Title, something like that.
स्वाति, फिर से repeat करो बेटा.
Ma'am, that we first give a like HTML, then head, then title.
No. That is coding. That part is coding. You're not getting my question. I said you have formulated a problem. You have identified the variables. Now you are trying to solve it on the system. Say, forget about the Mathematica part. Remove that. Come to some computer language, say Python or C or C++. So do you directly start writing the code in C++? या कुछ और करते हो जो करना चाहिए? Probably you people don't do. नहीं तो गलती कैसे पता चलती है? Say if you have committed a mistake somewhere, where would you find the bug? Huh? I mean, okay, even if you have to do coding, is there some procedure, some steps that need to be followed? Not exactly steps. I mean, some procedure to be followed. Ki, what is to be done after what? होता है कुछ? What is that called? अरे जल्दी बोलो. I can't. I want the answer from you. I will not speak. मेरे बेटे वो सब तो हो चुका. फंक्शन भी डिफाइन हो गया, मॉडल भी बन गया, वेरिएबल्स भी आइडेंटिफाई हो गए. मैं कह रही हूं अब तुम प्रोग्रामिंग करने बैठ रहे हो तो क्या सीधा कोड लिखना शुरू कर देते हो क्या? ये पूछ रही हूं मैं. Basic. What is the basic thing that you do before you write the codes or before you write the program? I mean, there are many of you who have studied computer science as GE. Come on, I want the answer from you.
Ma'am, like if we are given a question to find the sum of two numbers, and we have to
Yes.
do the coding of this program, then
Yes.
first we imagine like the sum of two numbers is a plus b.
Do you imagine or do you write it somewhere?
Yes,
It's
ma'am.
as
Like we
so when you write it
think it
somewhere,
like
what is it called? It is not a program unless and until you write it in the computer language. It is not a program.
yes, ma'am.
So before a program, when you write something, what is it called? Yes, fine. You're given a question. You are saying you imagine. If it's a simple thing, yes, you can imagine in your head. But if it's not simple, if it's complicated, you have to write it somewhere. What are you going to do? So that has a technical name. Before you convert, you have, in fact, you have a real life problem, you have a computer code. In between that also you write something somewhere and it has a name. I'm asking that.
I'm saving the file.
ये कौन बोला saving the file? You don't have to do an effort in that. Have you not heard of a term called algorithm? What is an algorithm? An algorithm is a stepwise procedure that needs to be followed, but not in a computer. Algorithm is never in a computer language. Algorithm is a stepwise procedure that the program is going to follow. That's what I'm saying. ये तुम लोग पता नहीं कैसे कंप्यूटर साइंस पढ़ते हो. You people straight away start writing the program and then you're not able to find the error in your program because you have not written the algorithm. You will write the logic somewhere. What logic is going to be followed? We did it in the last class. I called it an algorithm. Monte Carlo simulation is an algorithm. And you've all forgotten it. An algorithm is a stepwise iterative procedure because there are iterations involved, step by step, one after the other, maybe a repeated steps also, till we reach a certain stage. That is an algorithm. So when we say linear programming problems, basically the procedure of solution, when I say procedure, that means I'm talking of a solution procedure. So the solution procedure in these cases is, number one, going to be iterative in nature. That means we are going to repeat the things, we are going to repeat the steps till we reach a solution. I mean, we reach a solution means till we reach certain conclusions. You know, the conclusion can be we get a solution. The conclusion could be the problem does not have a solution. Any conclusion, but we reach a conclusion. So it is by means of an algorithm. That's why we call it as programming problems. There is no computer programming involved in it. I'm sorry. But we are using this term programming because the procedure that we are going to develop now is going to be iterative in nature. Again, a very common problem in MSc entrance interviews. Okay. Now, this term, the first, linear, is obvious in the sense that all the functions under study, be it the objective, be it the constraints, they are all going to be linear in nature. So they're going to be of degree 1. Okay, so all your variables in your study are going to be of degree 1. There is no degree 2, 3, or any other type of functions involved. Okay, so that's why we call such problems as linear programming problems. So as I always say, whenever you study a concept, every term in that concept has a meaning. It's just that you have to just understand. उसको रटोगे तो कभी याद नहीं रहेगा. But then if you understand, you'll never forget. Okay, so we have problems in which all the variables are related to each other in a linear manner, and the procedure that we are going to develop is going to be iterative in nature. Okay, now as I said, the linear programming problems, the solution procedure of linear programming problems is of 2 types. Number one is graphical and the other is algebraic. We can use any 2 methods to solve a given linear programming problem. Now, as we discussed in the previous classes, your linear programming problem has typically an objective function, right? Which is going to be either a maximize type or a minimize type of the form, say, z equal to, I'm writing it as Cx. I'll just explain it. What do I mean by this? I'm just writing subject to the constraints, which are of the form Ax either less than equal to or more than or equal to or equal to b. It can be either of these. And the fact that your variables are all non-negative. So we have the non-negativity restrictions also. Okay, so these, when I say subject to these system of inequalities, they form what we call as the constraints. This is your objective function and these are your non-negativity restrictions. So this is how a typical linear programming problem is going to look like. And in the previous exercise, you have formulated the problems also. So in a way, you have identified the variables from a real life situation that was given to you, and using the information, you have in fact constructed an objective function. You have identified whether the objective needs to be maximized or minimized because it has to be optimized. That's all. Then you have identified the constraints also, and you have listed them down depending upon the resources and the utilization of the resources. You have as many constraints to your problem. And for the solution procedure, because we are dealing with a real life situation, so for the solution procedure, we assume that none of the variable can be negative. So we assume the non-negativity restrictions. Okay. So as I said in the beginning, we'll be learning both these methods here, the graphical as well as the algebraic methods of solving a given linear programming problem. So we'll start with graphical first, and then gradually we'll move over to the algebraic. Now, the graphical has an issue in the sense that the graphical means what? You'll be constructing a graph. Okay. And when we manually make a graph, we are comfortable with only two axes, right? The x-axis and the y-axis that we had been calling it. So that means the first limitation when we are solving a given problem graphically is that maybe, on the horizontal axis, we can take one variable x1, and on the vertical axis, we can take the other variable x2, but then not more than that. So that means graphically, we can solve a given problem only if we have two variables. The number of constraints can be any, but variables have to be only two, because otherwise we won't be able to plot the graph. Okay. This is the major limitation with the graphical method. Okay. Of course, with, now softwares and things available to us, we can plot a 3D graph also. So maybe at the most we can move to three variables, but definitely not more than that. Okay. So the moment you have more than two variables, then we have to follow the algebraic approach of solving the given problem. Okay. Now, the thing is that it's very easy to understand the solution procedure graphically. But when we move over to algebraic, of course, it becomes a little, I wouldn't say difficult, but a little different, because you're not able to see it working, right? So but the thing is that whatever results or whatever theory we develop for graphical method, that is carried over to algebraic method. And of course, those theorems, those results, they are not violated. Okay. So to begin with graphical method, what we do is, like we have because of the non-negativity restrictions. Okay. So non-negativity restrictions means what? X1 is more than or equal to 0 and X2 is more than or equal to 0. That means when we plot the things and when we plot a graph, that means everything is going to happen in the first quadrant, because your x1 has to be more than or equal to 0. That means starting from the origin, it can move only in this direction. And x2 also has to be more than or equal to 0. That means only in this direction. So that means this quadrant, this quadrant, this quadrant is not of an interest to us. So we would be only interested in what is happening in the first quadrant. So this is the major advantage of non-negativity restrictions, that we need not bother about the values of the variables once it takes negative values. Okay. Now, before we move over to actually the method that we develop, we have to understand a few things, right? First is that we have constraints with us. And remember, constraints are inequalities here. Okay. So, like I could have a constraint like 3x1 plus 5x2 less than or equal to 9. Okay, so this could be one of the constraint, right? Now, to plot inequalities, of course, we know, had it been an equation, 3x1 plus 5x2 equal to 9, it's a straight line, right? See, my variables are this only. I have x1 axis, I have x2 axis. So can we not plot this line? How do you plot a straight line? बोलो.
With different values of x1 and x2.
हाँ, तो different में क्या लेते हैं? Conveniently, what do you take? Once you are given to plot a straight line, what do you do?
मैम इंटरसेप्ट फॉर्म से निकाल सकते हैं x1 के नीचे 3 और x2 के नीचे 9/5.
Or any other method? You are given to plot 3x1 plus 5x2 equal to 9. Or let it be 3x plus 5y equal to 9. How do you plot it? How many points do you need to plot a straight line?
Ma'am, 2.
So how do you find those 2 points?
Ma'am, we'll first keep x1 0 and we'll find the value of x2.
So what do? We just make a table. X1, X2. So once you put X1 0, then you put X2 0. So like in this case, when X1 is 0, how much is X2? 9 by 5. And when X2 is 0, how much is X1? 3.
3.
What are the points? So if this is 1, 0, this is 1, this is 2, this is 1, 2, 3. So what are the points that I'm going to plot? 0, 3. This is the, 0, 9 by 5. So where is the point 0, 9 by 5? Which axis?
x2.
Y-axis.
Y-axis or x2, right? So 9 by 5 means somewhere here. Okay, na? And what is the other point? 3, 0. So this is 1, 2, and 3. So this point. So what do? You just join them and this becomes the line. Is that right? इसी तरह से करते हैं ना?
Yes, ma'am.
But then this is the straight line. 3x1 plus 5x2 equal to 9. But our constraint is less than or equal to 9. So how do you plot this less than or equal to? How do you plot an inequality?
And the area that is under that line and bounded with x-axis and y-axis.
How do you find the area, whether it is going to be under the line or it is going to be above the line? How do you ensure?
Ma'am, we'll check.
अगर origin उसको satisfy कर रहा है inequality को.
You just satisfy whether, see, this line has divided my first quadrant into two parts, this and this. As far as this part is concerned, the origin lies here, right? So what I do, I just check whether origin satisfies the inequality or not. Now, when I put 0, x1 0, x2 0, what is my left hand side? 0. And 0 is actually less than or equal to 9. So that means what? The origin satisfies this inequality. That means the origin lies in the region covered by this inequality. Okay. So that's how you shade it, right? So this becomes your region. For the, see, inequality is not just one line. Inequality is number one, a region, right? Equality is a straight line, because equality means all those infinitely many points that lie on this line are going to satisfy this equation. But inequality means all those infinitely many points that lie in this region are going to satisfy this inequality. Is this clear? So inequality means we have to identify the region, right? Okay, now as far as the one inequality is concerned, I am able to identify the region. But my linear programming problem does not have just one constraint. It may have 2, 3, 4, any number of constraints. So that means when I am talking of constraints here, I am actually talking of inequalities. Some may be less than or equal to types, some may be more than or equal to types also. But when I'm trying to solve the problems, when I'm going to solve the linear programming problem in particular, then all the constraints need to be satisfied simultaneously. Okay, that means I'm looking for that value of x1 and that value of x2 such that all the inequalities are going to be satisfied simultaneously. Okay, so that means when every inequality is going to give me a region, ultimately that region is going to be sort of, it will turn out to be sort of a closed kind of a structure, in the sense that, say, supposing I'm just giving a very, a rough, maybe, one constraint is this. When I plot the other constraint, it becomes this. And so supposing it has another constraint and it becomes this. Okay. And so supposing all the three were less than or equal to type. So say supposing this, shall I use different colors or is it okay? So supposing this was your first constraint, so I'm numbering it. This is 1, this is constraint number 2, and this is constraint number 3. Okay, see, constraint number 1 had this whole region with it, right? But when I plotted constraint number 2, my region actually became this, right? Now see, this region specifically, though it is being satisfied by constraint number 1, but not by 2. Similarly, this region, it is being satisfied by constraint number 2, but not by 1. So what is left is, I'll just find the common one between 1 and 2, which is this, right? But when I plot the constraint number 3 also, this region is now only this much, right? So what has happened? The common region that's common region means all those possible coordinates x1, x2, they are infinitely many in the first quadrant, right? So all those infinitely many points that satisfy all the three constraints simultaneously is getting reduced, but still it is infinitely many, right? But then you see what is happening is you are actually getting a region something like this. Says, let me say something you are getting something like this from here. I mean, of course, the things cannot go beyond x1 and x2 because they cannot take on negative value. So this is my constant number 1, and constant number 2 though has been left somewhere behind. So this is my constant number 3. So basically now I am interested only in this region. Okay, this common region, that you get of all possible x1, x2 combinations which satisfy all the constraints simultaneously, this is called as a feasible region, because this is going to give you a solution that is going to be feasible. See, when you have system of equations, you solve them, right? So maybe system of equations is consistent, maybe system of equations is inconsistent, right? When you have a system of equations which is being consistent, that means you say a feasible solution exists. Similarly, here we do not have one solution because we have inequalities. So we have what we call as a region. Okay, so this feasible region is, I mean, depending upon the nature of constraints, the signs in the constraints, this feasible region is always going to be what we technically call as a convex set. Okay. Now, to give you an idea what we mean by a convex set, we say that a set is said to be convex, if for any 2 points lying in that set, okay, the line joining those 2 points also lies in that set. Okay, so basically, if you have any 2 points, say x1 and x2 from any set, then line joining points means the convex combination. See, you have heard of linear combination, right? When you say linear combination, it's like a1x1 plus a2x2, right? But we have a convex combination such that lambda x1 plus 1 minus lambda x2. Any linear combination is said to be a convex combination if the sum of the coefficients is 1. Okay, so if the sum of the coefficients has to be 1, so if that means if a1 is there, then my a2 has to be 1 minus a1, because I just have 2 variables. Okay, so in this I can straight away write like this. So if x1, x2 belong to any set, then lambda x1 plus 1 minus lambda x2 also belongs to that set. Then such a set is said to be a convex set. But what do you graphically mean by a convex set? Like, for example, say supposing you have something like this. Say this, 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 this. Okay. Now this has A, B, C, D, and E, 5 vertices. Now you pick up any 2 points in this region, you will see that the line joining those 2 points also belongs in this region. Okay, so this is kind of a convex thing. But if you look at something like this, say supposing you have, this is also possible, right? So it has A, B, C, D, E, F, G, and H, these many vertices. But in this set, if I pick up a point here and I pick up a point here, say supposing this is my x1, this is my x2, this is the straight line joining x1 and x2. And this does not belong to the set. Okay, so this region, this kind of a region is not convex. Is this clear? Now, if you just go back to the kind of feasible region that I plotted, you can easily see that this has turned out to be, it's like a quadrilateral, right? So it is a convex set. Now, the theory that has been developed and it has been proved, we are not going to do the proofs here, but it has been proved that the feasible region for any linear programming problem will always be a convex set. Okay, so that's why all the theory, that we have done so far can be converted into a linear programming problem. Is this clear?
Yes, ma'am.
Okay. Now, the thing is that once you have identified the feasible region, that means we have covered the constraint part and the non-negativity restriction part as well, because we are in the first quadrant. Now, what remains to be handled is the objective function, because our problem was either to maximize or to minimize, or in other words, our problem was to optimize the given objective, right? So now to handle the objective part, what we do is there is a theorem. Again, there is a result that has been proved. Now, of course, the obvious question could be, the obvious logic could be, okay, if this is my feasible region, that means one solution out of this region is going to satisfy the objective. Satisfy the objective means it is going to give me a maximum solution if it was a maximization problem, or a minimum solution in case it was a minimization problem, right? But then definitely it has to be a solution from the feasible region also. That means, in a way, what we have done is we had so many options to choose the solution from, but in a way we have restricted it to only this region. But even this restriction is of no use to us, because how many points are there in this region? Infinitely many. So I cannot be checking for every point in this region and then say whether it is going to optimize my objective function or not. Okay. So for that, a theorem has been proved. If you see the theorem 1 on page number 262, okay, which says, I'm not writing it as verbatim, but I'm just giving you the crux of that theorem. You can always see that theorem. So this is what this theorem says, that if you have a feasible region, okay, which is bounded and convex, number one, okay, and of course non-empty, okay, non-empty because we want a solution to exist. We'll consider these where we have different types of solutions. Convex, bounded, non-empty. Then the objective function, will obtain, the objective will obtain its maximum or minimum value, depending upon what is your objective. It will attain these values at the extreme points of this feasible region. Okay. See, now this is a very important breakthrough, because the moment we say extreme points means what? The vertices of that convex region, right? So that means we need not bother about all the infinitely. See, this was my feasible region here, right? Which had infinitely many points, right? But as far as the extreme points are concerned, they are limited. I have this as one vertex, which I can call as O. This is another vertex, let me call as A. This is another vertex, let me call as B. And this is another vertex, let me call as C. So I have only 4 extreme points for this feasible region, compared to what? Infinitely many, right? So though you had been doing it like this, but I think no theory was discussed in class 12. So, but then this, of course, right now we are also not proving, but maybe, you know, in the next semester, if you take up this DSC, we'll actually prove that the optimal solution exists only at the extreme points. Okay. So once you have extreme points with you, it's easier now. What you have to do, you just identify the coordinates for each of these extreme points. O, we know 0, 0. A is a point on the x1 axis, so we know the coordinates. B is going to be the intersection of two lines. We can always find the coordinates. Similarly, C is going to be a point on the x2 axis. We can find the coordinates. So basically, what we'll have now is that we'll have the coordinates of all the extreme points with us. Okay. Now, that means we can compute the value of the objective function at these extreme points. Okay, at O, what will be the value? At A, what will be the value? At B, what will be the value? And at C, what will be the value? Okay, out of all the values that you obtain at this, if your objective function was maximum type, then you'll pick up the maximum value of Z. Okay, so that will be your optimal solution. Okay, see, there we'll be calling, I'll be just explaining this also. That will be my optimal solution. Now, what do you mean by optimal solution? Optimal solution means the maximum value that your Z can obtain. That becomes the optimal value of the objective function. And the I mean the solution. Solution means what? The coordinates. At what point is that maximum value being attained? That becomes your optimal solution. Now, that means, see, we in fact, you know, we always find what we call as the optimal feasible solution. Okay, I'm not writing the word basic in between because we have not yet done the algebraic part. Okay, so we'll come, otherwise we have a term called as optimal basic feasible solution. So right now I'm neglecting this term. Okay, so solution means what? Again, read it backwards. Solution means all those possible values of x1 and x2 that satisfy your constraints. Okay, and how many are there? Infinitely many. That means, I mean, or you can say all the possible x1, x2. Feasible means all the possible values of x1, x2 that satisfy all the constraints simultaneously. Is that clear? So that means though they were infinitely many here, they are infinitely many, but less than this. Still infinitely many. Okay. Basic means all those x1, x2 which lie at the extreme points. Okay. And optimal means all those basic feasible solutions that optimize the given objective function. So we have, that means optimal feasible solution. Every optimal feasible solution need not be an optimal basic feasible solution, because basic means we are only talking of the, or did I say the, I mean, I think I'm saying the other way around. Optimal basic feasible solution means those solutions which are at the extreme points of the feasible region that optimize the given objective function. Now, is this clear or not? Because this is very important, when we talk of these terms here. Is this clear or not?
Yes, ma'am, clear.
Okay, so that means now when you are trying to solve a problem, you have to construct, of course, you have to construct the problem first. That is your first step. Then plot the feasible region, right? Shall I write it? Okay. So what we are going to do is, your step number 1 is construct the problem. Construct the problem means the way you did it in the previous exercise. Okay. Convert the real life problem into a linear programming problem, right? Then plot the feasible region. That means plot the constraints and identify your feasible region. Matlab, that region which satisfies all the constraints simultaneously, right? Then identify the extreme points. The points that lie at the boundary, the vertices of your feasible region. And then find the optimal solution. Okay. So optimal solution kaise aayega? Substitute, find the value of the objective function at all the extreme points, and then identify the optimal solution. So when you write the optimal solution, you have to write the complete solution, in the sense that, see, solution means x1 equal to something and x2. See, solution means you are telling the decision maker that he should make these many units of x1 and these many units of x2. Okay, so you have to identify this is the solution, and also at the same time write what is your maximum revenue. Okay, so depending upon what kind of problem you are handling with. So this is how the problems need to be handled. Is this clear?
Yes, ma'am.
Yes, ma'am.